So we're starting here on page 31. And we've been talking about the normal approximation, which is very useful for data that follows the normal curve, because all we need are two summary statistics, the average and the standard deviation, and we're able to figure out percentages within any interval. So let's look at this example here. And what does it say? According to your survey data, the histogram for the fastest speed ever driven is close to the normal curve with an average of 90 and a standard deviation of about 24 miles per hour. So this is after I actually removed the 120 people that said they drove 0 miles per hour. 120 people said they'd hadn't driven, and 320 have driven. So altogether, about 440 people answered the survey for Stat 200, and 320 of them have driven, but 120 haven't. That's a big percentage. I was surprised. So what I did was this only includes the 320 people who've driven. Otherwise, the data really looks like has a big spike here at 0, and then approximately follows the normal curve. So I removed that spike there because we couldn't use a normal approximation unless our data is normal. So if you just look at the people who've driven, it's about that. So about 95% of the class would list their fastest speeds between what and what. Well, remember this 95%? If it follows the normal curve, then we have about 95%. We have that rule of thumb that about 95% is between, do you remember what? Between z equals -2 and z equals 2. But you don't want to put between -2 and 2 in there, right? You want to put what? Between what? This is 2 standard deviations from the average. So the average is 90. So we want to go up down to the lowest limit would be -2 standard deviations for there. So that would be -2 times 24. And here would be 90 plus 2 times 24. Okay? Does that make sense to everybody? So that's what? So this is just the average minus 2 standard deviations and the average plus 2 standard deviations, which is between 42 and 138. All right. So now I was going to let you do some of these examples on your own, but since we're just starting with this page, I'll do the first one for you here. And then you'll do, because we have a lot of examples and we already pretty much covered this. So to remind you, let's just do the first example. So let's say one student listed her fastest speed as 114 miles per hour. So about what percentage of the class listed faster speeds than her? What percent would have listed faster speeds than her? Well, how would we figure this out? Our very first step is always to always convert your value to a z-score. That's what you always want to do. So you've got a value, and you have to change it to, this is our value, you want to change it to a z-score, and then you want to use the normal curve. That's the roadmap here, right? So we have our value of 114, and we change it to a z-score by saying z is equal to, let me get a better, this is running out of ink. Let's see if this is better. So z is equal to, remember, it's our value minus our average over the standard deviation. Value minus the average over the standard deviation. So in this case, it's 114 minus 90 over 24, which turns out to just be 1. So that is our z-score. So here's the normal curve, so we know where to mark it. Mark it right here. So this right here is where 114 is, and it's a z-score of 1. So now, what do we want? What percentage do we want faster than her? So that would be this percentage right there, faster. So what is that? Well, remember, to use our normal approximation, we have to, the table that we have, that's what we're using, and we can find it at the back of the book. The table is right here. And you should know between 1 and -1, that's one you should know, it's about 68%. But if you didn't, right here, 68.27. Okay? But we're just going to round to 68 so we can do these in our heads. Follow the directions in your homework. Just follow the directions given. I think on some of the problems they say to round to the nearest whole number here as well. Okay, so between z equals -1 and 1, we have 68%. So what is the area here? The whole thing's 100. So the area that we want was 100 minus 68, 32 over 2, which is 16%. So that's 16% right there. So now, what percentile is she in? Well, what percentile would she be in? What is the percentile? It's this percentile is all the area to the left. So the percentile is equal to the area below. So the area to the left. So all this area is the percentile. That's what the percentile is. So what percentile is she in? So it's, what's that area? That would be 68% plus 16%, which is equal to 84%. Okay? And those two have to add up to 100. So I'll let you do the next two on your own. So this is what percent of the class never drove above. Let's do a really easy one you could do and in your head. And if the fastest I've ever driven is 0.5 standard deviations below this class, what's my fastest speed? So why don't you do the rest on your own? Okay? And when I say do on your own, if you're going to be turning your notebook in for bonus points, you should be doing these because we'll check these. All right? And I'll post any ones I say do on your own. I'll send you a picture of the worked out solutions later, at the end of the week or something, or later, so you can check your work. Okay? So do it on your own. It's good practice, and then you can check your work. So now we're going to be talking about percentiles, and we just said it's all the area below a particular value. So why are they important? Well, as previous chapter shows, well, this is wrong. We haven't really talked about this, but the average and the standard deviation are not always enough to provide an informative numerical summary of a data set. So in these cases, percentiles can be useful, but that's when the data when the data is skewed, when it doesn't follow a normal curve, okay? So when the data doesn't, they're not all, so this is, let me just say this. So when data does not follow the normal curve, the average and the standard deviation aren't enough. And so we would have to give you more information. So let me show you. So let's look at, for example, let's say C, page 19. And let's look at page 19. When it doesn't follow the normal curve, these percentiles are often very useful. So for example, here, this doesn't follow the normal curve. So if I gave you the average, this is page 19. Is that what I said, page 19? So this is, so the average and the standard deviation, just giving you that, wouldn't help you figure out the different percentiles. So I'd have to give you more information. So for example, on here, if I asked you what the 70th percentile is, what would be the answer? You have enough information here. Like, what's the 70th percentile here? So it would be 70% would be below. That means 30% would be above. So your answer would be 80. Does that make sense? Because 70% is below and 30%. 25 plus 10 is 35, 45, and 25 is 70% is below. Okay? So if I asked you what's the 35th percentile, the 35th percentile, what would you say? 35th percentile. Oh, you're here to finish this, to fix this? Yeah, could we take let's just answer this question, then we'll take a few minute break. And so this would be 60, the answer. All right, let me see if there's anything I can explain while you're doing that. So we're going to go back to where we were, and that's right here. Okay, so just could you wait a few minutes? Okay, so, but when the data does follow the normal curve, the average and the standard deviation is enough to give you any percentile. Okay, gives you the percentile. How? Well, through the z-score, So what you do is you just say, okay, value, right, through the z gives you the percentile, like we've just been doing. Okay, so we can do this easy one here. Let's say you had an average of 7 and a standard deviation of 1 for here. And this is actually pretty much what our data is. Follows the normal curve, number of hours people sleep, with an average of about 7 and a standard deviation about 1. So a student who only sleeps 5 hours per night, you have your notebooks here. See if you can do this one on your own while she's fixing that, and then we'll make sure you get, and let's change this, I'm going to change this to 60th. So do these two on your own. You have enough information. You have a value, change it to a z-score, and then get the percentile on here. And then to do this one, you're going to have a percentile, right, on the normal curve, and you're going to do the same thing. You're going to get a z-score and then find the value. This is a little bit harder, but see if you can do these two while she's fixing the computer. So I'll give you a few minutes to do that. Go ahead. Yeah, so when we go to, okay, so if we go to the PC, it just doesn't work. See, it says no signal. Okay. And I turned the PC on and off, okay. And I check, I mean, I don't want to mess around with the wires. Maybe something's disconnected. Oh, wait a minute. Yeah, is that supposed to be connected? Like right here, that's what happened. That's not connected, right?
No, this is different. This is
oh, that's for a laptop?
That's for a laptop.
Yeah.
And so yeah, these are all laptop cables. This one, so it's
maybe the back of the
internal,
computer?
Yeah, it's probably an internal problem. But they make us check it out first. If it's not working, then we have to call like a more professional technician.
Okay.
So,
you're just going to try disconnecting some wires first?
Check. But see, look how it's all internal. So if it's an external thing, then we can fix it, but otherwise we have to call the actual technician, but they always make us go out and check.
Okay, so you think it's internal?
Yeah, I think it's internal.
All right, that's okay. I don't really need to use it today. I was just going to display one thing, so that's okay. So I'll go back to the, thank you for coming.
No,
that's really appreciated. You know, probably the next person who comes in at 11 is really going to need it.
Yeah.
Because almost everybody uses this.
Yeah.
So it would, yeah.
I'll just put in the request and see how fast it'll be when they can get something.
Okay, but I'm going to be using this. They won't be able to do it till 11.
No, I understand.
Yeah. Okay. All right. All right, guys, so we can go back. It turns out the computer's not working today. That's okay. We're just going to be dealing with the notebook. Just check the calendar and check your lawn cap, and you'll see what's open and what's upcoming. All right. So now, so what did you get here? Did you get how many people got 2.5%? Did you get that? Good. So let's just see how you do this. All right, so our value is what? Our value is 7 hours right here. No, average of 7. Our value is right here, 5 hours, right? So 7, here we have 0, 1, 2, 3, -1, -2, and -3. We know 7 hours is right in the middle here, and we just want to know where to place 5 on here. So we say 5 is our value, and we want to change it to a z-score. So you just say 5, our value, minus the average over the standard deviation. So that's -2. So we can write right here. This is -2 right here. So -2, and then what percentile is that? Well, percentiles, everything below. So between 2 and -2 is approximately, you should know this, 95%. If you don't, you could look it up. And so then this area right here, our percentile is 2.5%. Does that make sense to everybody? That would be the answer. 2.5% of the people in the class sleep less than 5 hours. Any questions on that? Now, let's say you're at the 60th percent. This is a little bit, we're going in the opposite direction. So now we have to locate our first step. We have the percentile, so we know that's 60th. And now we have to get a z-score. So how can we do that? Well, first let's remember that right in the middle, right here, what percentile is that? What percent is below 0? Isn't it 50th? So that's your 50th percentile. All right? So let's just put 1, 2, 3, -1, -2, and -3. Now the 60th is going to be how far above that in terms of percents? We have 50% here. We just want to add 10%. So I can just draw it in approximately. I want to add 10%. And that will bring me to the 60th, correct? All right. Now, to find the z, that z right here, what do I have to look on the table that we're using? I have to find this z, I have to do what? I have to find the middle area. So I have to ask myself, what middle area should I look up to get that z? This is the z I want. So what's the middle area? That says, what middle area should I look up? Well, we have to make it symmetrical. If it's 10% on one side, it's going to be 10% on the other side. That's 10 on each side, 10 and 10. And so I want to look up a middle area of 20%. Does that make sense to everybody? So now I want to look up a middle area of 20%. So let's do that. And what do we get? So you look at your area and go to the line closest. 20 is in between 19.74, but it's and 23.58, but it's much closer to this one. So we're just going to go to the closest line, and so that's 0.25. Okay. So 0.25 is the z-score here, and -0.25. So it's one of those two z-scores. 60, you can see because 60 is above the 50th, it's going to be positive. So it's that one. So our z-score, our z is above 50, or above 50th. Everything here is positive, so it's positive 0.25. Okay? So that's now, what do I want to do? I want to get the value there. Well, how do I go from it? This tells me what? This tells me the value is going to be what? I'll start at the average, because that's what 0 is. Right here, the average is 7. I'll start there. And then I'm going to add to it, what am I going to do? 0.25 times the standard deviation. right? So I'll start at the average 7. I want a value. I'm trying to get hours here. I have a standard units. I want to get hours. So I say 7 plus 0.25 times, these are hours. 1 hour is a standard deviation. This is hours. Now I'm in hours, and it's 7.25 hours. Okay? Now, what if I'd said the 40th percentile? 40th. Do you see how you could use the same picture? Because the 40th is going to be just as far below 50 as the 60 is above, right? It's completely symmetrical. So if I did the 40th, then what would happen? Then my z would be what? I'd have the same picture, but my z would be what? Negative, because I'm below average. It would be negative 0.25. And then my value would be what? Then my value would equal, I'd start at the average and add negative 0.25 times 1, or subtract that instead of adding, because it's negative. It's the average plus z times the standard deviation. So my answer would be 6.75 hours. In other words, they're completely symmetrical because 40 and 60 add to 100, so they're going to have opposite z-scores. Any two percentiles that add to 100 will have opposite z-scores because they'll be the same distance above and below the average. Any questions on that? So that's basically the way that you would do these problems. And I think, let's see, over here. Oh, yeah, sure. How did I get the 20% in the middle? All right, so how did I get this 20% in the middle? Well, I want to get, my percentile is 60th, okay? So I'm asking how far 60th, right in the middle is 50th, because it divides it into 50% on each side. So how far, what percent, I'm trying to get a middle area, so 60 minus 50 is 10. So that gives me half the middle area. That gives me this half. And so I have to do it on this, to be symmetric, I have to get that half too. The only reason we're doing this is because of the table we're using. Remember, our table only gives this middle area right here. And so what I was saying was I got half of it. This is 0, and that's the 50th percentile. So whatever percentile, like if I was looking for the 70th, let's say the 80th percentile, then it would be 30 on this side, 30 on that, and so it'd be 60 in the middle. Does that make sense? Any other questions? Another way you could do it is that the tails be the same, too. You could figure out and make the tails symmetrical. Just whatever comes to you, but it just, the idea is that you're just as far above when you're in the, let's say you were in the 80th percentile here, it would be symmetric with the 20th. Those two add to 100, and you're just as far above, you're 30% above average, and here's 30% below average. So they're going to have opposite z-scores. It's because of the symmetry. Does that help, everyone? And so that you'd look up 60 in the middle if you wanted to find the 80th percentile. The 80th percentile would also have, if you looked at the tails, you'd have 10% here. Excuse me, 20% here. 80th is all the way 80, and you'd have 20% there, which would leave 60 in the middle. That's another way to do the same problem. All right, does that help people? Okay, 80th means all the way to there is 80%, and 30th would mean all the way to there. So if you're looking from the bottom, a person in the 30th percentile is 20% from the bottom, and a person in the 80th percentile is 20% from the top. It's just the symmetry of the curve. Thanks for asking questions. All right, so now let's go back and we'll do another problem. All right, so according to last semester survey data, the histogram for the weights of the females in our class in Stat 100 was 134 pounds with an SD of 24. And the weights approximately followed the normal curve. So what weight corresponds to the 15th percentile? Okay, so we're given the percentile right here. Given the percentile, we're going to go from percentile. You have to go through the z-score to get the value. And if you go in the other direction, you have to go through the z-score to get the, so your z is the connector between these two. All right, so what do we know here? We know 0's in the middle, and that's our 50th. And percentile. So the first thing you're going to think about is, okay, 15th. That's below. So we know it's going to be a negative z-score. We know right away it's going to be negative because it's below. So it's going to be, this is -1, -2, -3, etc. Okay, so the 15th, you could either say 15 in this tail and 15 in that, just because that's probably easy to do. You could do it that way. Or you could say the 15th is 35% below. This one just means directly, I think it's easier to do this way, that this means 15% is below. And so that would mean 15% here to make it symmetrical, and that would be 70% in the middle. Another way you could do this would be 35, 15 is 35 below 50, 35, and together they're 70. The same thing. All right, now I didn't approximate it really well. I have to look up 70 in the middle, and I happen to know that it's -1.05. I'll show you. Because 68 in the middle, right, is 1, between 1 and -1. So 70 in the middle. All right, it's a little bit less than 1 because 70 is between those two, but that's okay to use the nearest line. So we're just going to go with 1.05. So that's where I got that from. So 70 is between 1.05 and -1.05, which makes sense because between -1 and 1 is 68. All right, so we've got the middle area here. And now, so we said, remember what middle area? We got the 70. I'll write this down just so you remember. What middle area? That's what you ask yourself. And we got 70%. And then we found the z is equal to, now you could 1.05, but it's negative because it's below. All right? And so now what's our value? Our value is, remember, the value is just going to be, I always start at the average, right? And then it's going to be plus z times the SD. That's the same as the other formula. Value minus average over standard deviation is equal to a z. But this is very intuitive. So to get our value, we start at the average, which is what? 134. That's a z-score. Now we're going to go down, so plus -1.05 times our standard deviation of what? 24. So we're going down. Here's the average. That was 134. And we're going to go down a little more than 1 standard deviation. So that's 134 minus what? 25.2 pounds. So that's 108.8 pounds. Now, if we wanted to do the symmetrical one, watch, we could draw the same exact picture, and now we're at the 85th percentile, right? This percentile right here is the 15th, and then 50 plus 35 is the 85th. So that would be our, so now we're doing the same thing. We're going percentile to the z to the value. And the percentile is 85th, right? And then we get, right here, we're going to get the same picture. It's the same exact picture as above. This is the same picture. It's that one. All right, so we get 1.05. It's positive because it's above. That says 85. And so now what are we going to do? We're just going to start at the average, 134, plus, instead of, we're going to add 25.2 pounds, plus 1.05 times 24. So that's 134 plus 25.2, and we get 159.2 pounds. So the basic idea is that there's a symmetry here. So if 2 percentiles add to 100%, then they have opposite z-scores. The same number, but opposite signs. Okay? Any questions on that? All right, now I think we can do this. This is good practice, so this is going to be another. This is another. These two are do on your own. So I'll just say do on your own. For bonus points, if you want, if you're turning in your notebook for bonus points, be sure to have this filled in. And again, I'll post these answers and the solutions so you can check your work. But it's going to be very similar to that. So I don't think I need to do both, and I think this is good practice for you. All right, so now let's move on. And so the summary here, this is all very good. So I'll just say read, and I'll just add this when the value, okay, to figure out the percentile from the value, you do this and go the other way. Or if you start with the percentile, just go the other way to get the z-score and then the value. Okay, so that's it for the normal curve. That's it for the descriptive statistics. We're going to revisit the normal curve because, as I said before, it's going to come up a lot in inferential statistics because it's the distribution of means. When, if you took a sample from a larger population and computed its mean and did that over and over and over again, you'd expect right in the middle of the histogram to get the mean of the population. And then but you'd have a distribution of means around that because you would get different samples each time that would resemble the normal curve. So it's going to come up a lot. But as the bridge to inferential statistics, what we're going to do now as the bridge is probability. Because inferential statistics is looking at numbers that are generated by some chance process, either random division into treatment and control or random sampling from a larger population. And so we have to develop probability models and look at how the laws of chance work so that we can, from them, derive statistics and distributions for inferential statistics. Okay? So it's going to be our bridge to inferential statistics. So this probability that we're going to do is very simple, and I bet a lot of you have already seen it. So we're just going to try to cover chapter 6 today. So let's see. All right. And this homework is for the normal curve is posted, and it's homework 4, and it will cover chapter 6 as well. And the pre-lecture for chapter 6 is posted, And the one for Chapter 7 is posted as well. And that's not due till a week from this coming Friday. So you have a lot of time to do all that. All right. So we're going to start off with this definition of a sample space, and that's the set of all possible outcomes of some experiment, or some set of all possible outcomes. So for example, what would be the sample space when you roll a die? It's all possible outcomes. Well, you could just get a 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, or 6 spots. Okay, and the definitions of probability, okay. So the probability of an outcome is the percentage of times one expects that outcome to happen when the process is repeated over and over and over again under the same conditions. That's one way of looking at it. Another way is the probability of an outcome is equal to the number of that outcome over the total number of possibilities. So this would be the total number of possibilities, would be your sample space. And then you just count how many of the outcomes fit your whatever event you're thinking of. So for example, what's the probability of rolling a 5 on a fair die? Well, we just said the total number of possibilities is 6. And how many of these? What's the number that could be 5? Just one of these. So it's just 1/6. And that's pretty easy. So what's the probability? We're going to look at some cards. So what's the probability of getting the Queen of Spades? This is my attempt at a spade here. Okay, so what does a spade really look like? It looks like that. Okay, so the Queen of Spades, there's only one, there's 52 cards in a deck. And there's only one Queen of Spades. Okay, so it's 1 out of 52. Maybe I should write that with cards right here. Cards, okay, there's a 52 total in a deck for those of you who don't play cards. And then there's these 4 suits. And there's 4 suits. And the suits are hearts, diamonds, these spades, and clubs, which look like that. Okay? So the clubs look like a clover. All right, so those are the 4 suits. And there's in each one of these suits, there's 13 cards. So there's like a 2, 3, through 10. And each one, and then there's a jack, a queen, a king, and an ace. So there's 13 in each one of these. So there's 13 cards in each suit. Two through 10, and then jack, queen, king, and ace. All right, so that's the idea. All right, so now, those of you who've never seen a deck of cards. So now what's the probability of drawing a queen? Well, there's 4 queens. There's going to be a queen for each one of these. So the probability of drawing a queen would just be 4 out of the whole sample space, 52. And how about an even number with a fair die? These are really simple. The probability of an even number would be what? The probability of an even number would be, there's 3 even numbers, 2, 4, and 6 out of 6. And you can write that as 3 out of 6 or 1/2. By the way, when you enter your numbers on probabilities on ln kappa, you don't have to reduce fractions. It will accept any equivalent answer. All right. So now probabilities range from 0 to 1, or if we're talking about percents, 0 and 100%. So what is this complement? Okay, so sometimes, okay, so the probability, we'll write this, the probability of A is equal to the probability that A happens. Okay? And then there's something called a complement, and we write it this, the probability of A complement, and that is the probability that A doesn't happen. And we're talking about events that either happen or they don't happen, right? They happen or they don't. So that means that the probability of A plus the probability of A complement is equal to 1 or 100%. All right? So the reason why this is important, you'll see later, is because sometimes one of these is easier. Sometimes A is hard to figure out directly, and so we could figure out A complement, okay? So that's the same thing as saying the probability of A, this is the same thing as the probability of A is equal to 1 or 100% minus the probability of A complement. And if this is easy to figure out and this is hard to figure out, then this is a nice way to do it. In these cases, they're kind of equivalent. So we know that the probability of 5 is 1/6. So the probability of not a 5, that's the complement, of not a 5, is going to have to be 5/6, 1 minus 1/6. They have to sum to 1. This is very easy to figure out directly, though, because you could figure out directly, there's 6 possibilities, right? 6 of them, and only 1 and 5 of them are not 5s. So you could figure that out directly. So same with this. The probability of a queen, we said, is 4 out of 52. So the probability of not queen is going to be 1 minus 4 out of 52, which is 48 out of 52. They're complements. They have to sum to. This one, again, is easy to figure out, but that's the idea. So now on page later, we're going to see, so it's useful when the probability of A is hard to compute and the probability of A complement is easy. And that we're going to see examples of that on page 37. We'll see 2 classic examples of that. Okay? Any questions so far? All right, but before we do that, let's look at this key idea in statistics of independence. You're going to see all the time when we make these, the assumptions that we're going to make all the time when we're figuring probabilities is that, like if you're doing sampling, that one draw is independent of the next draw, or that your errors are independent. You're going to see this all the time as an assumption, and it means that what you get on one draw doesn't affect what you get on another draw. For example, if you roll a die, what you get on the second roll is independent of anything you got before. The die has no memory, and just because you got a 1 the first time doesn't influence at all what you're going to get the second time. And so that's true with most gambling games. One exception is cards. So let's look at cards to see the difference between independence and dependence. That is an easy one to think about. So with and without replacement. First of all, 2 events are independent if the probability of the second happening is the same, regardless of whether the first happened or not. And 2 events are dependent if the probability of the second event changes, depending on whether the first event happened. So rolling the dice is always going to be independent, but what you get on one roll does not at all affect what you get on the other. But if you draw without replacement, then the chances change, okay? And if you draw with replacement, they don't. So for example, if you draw 2 cards with replacement, is getting a heart on the second card independent of getting a heart on the first card. So the probability of getting a heart on the second draw is equal to what? There's 52 cards. Whatever I get on that first card, whether it's a heart, there it was a heart, and I stick it back, or it wasn't a heart and I stick it back, does it matter? Does it affect the chances on my second draw? No, there's still 52 cards in here, and there's still 13 hearts in here. So those events are independent. So they're independent. Yes, independent. Because why? Chance is the same. The probability is the same, regardless of what the first card is. Because it's stuck back in the deck. So it becomes just like dice, right? Just like a die. But what about if we do the same thing without replacement? Is getting a heart on the second card independent of getting a heart on the first card? Well, no, it's not. Why? It's dependent. Because the chances change. The probability of a heart on second card if first is a heart is what? Okay, so if the first was a heart, let's pull out a heart. Let's say we got a heart, and we don't put it back in the deck, right? Now there's only 51 cards, and there's only 12 left. But the probability of a heart on second card, if first is not a heart, is equal to what? There's still 51 cards left, but if we pulled out something that wasn't a heart, then how many? We have 13, so they change, okay? So it changes depending on whether the first card is or not. No, dependent, because probability changes depending on whether, depending on whether or not the first card is a heart or not. Okay, so that's the idea. And now there's this multiplication rule. Okay, so there are two things. Okay, so what is the multiplication rule? Where can I put it? All right, so this was the independence. Now, this multiplication rule, oops, right here, this is what I'm talking about. So what is this multiplication rule? That if you want two things to both, if you're looking at the probability that two things both happen, you multiply probabilities, right? If the chance of getting a 5 on the first roll and a 6 on the second roll, if you want both those things to happen, you're going to say 1/6 of the time you get a 5, and then 1/6 of the times that you got, now you've gotten the 5, and 1/6 of those times you might get a 6. So it's 1/6 times 1/6. The probabilities get smaller when you want both things to happen, right? So you'd think, oh, both things to happen, probability of A and B is going to be the probability of A plus B. No, it's the probability. So the multiplication rule is that the probability of, what does it say? The probability that two events will both happen, so that's the probability of A and B both happening, is what? Is equal to the probability the first will happen, the probability that A will happen, times the probability that B will happen, given that A already happened. That says given that A already happened. You read that as probability of B given A. That means the probability of B, that line means given A has happened. Okay, so that's the general rule. But if two events are independent, so if two events are independent, then it can simplify then it will just be the probability of A times the probability of B. Why? Because this, if they're independent, then the probability of B is the same whether A happened or not. Okay? So let's write that down. That's the same thing. So when you have independence, you could use that, but it simplifies. When independent, you get the probability of A and B is equal to just the probability of A. And you don't have to think about whether A happened or not because it doesn't affect the chance of B. Right? Since the probability of this B given A is equal to the probability of B. It doesn't matter. All right? So we can look at this now. And let's look at an example. So a box has what? Let's write it down here. A box has, we have a box in here, and we have tickets, and we're going to shake them up, but it has red, red, and red, 3 reds, 2 blues, and a yellow. Okay? And we mix them all up. And now, what's the probability of drawing 2 blues from the box with replacement? Now, with replacement, they're going to be independent, right? They're going to be independent, so it's just going to be the probability of blue and blue, B and B, sorry. Probability of B and blue is just going to be 2 out of this. There's 6 tickets, and 2 of them are blue, so we get a blue, but we put it back. So it doesn't change anything. So it's just 2 6 times 2 6. You can write it as 1/9 if you want, but you don't have to. All right. And now, but what about without replacement? Then it's dependent. The 2 events are dependent. So the probability of blue and blue changes. It's still 2 out of 6. The first blue is still tied, but now you don't put it back. So you're going to multiply it by something. You're going to multiply it. Now there's only 5 outcomes. And now it matters whether it was blue or not, right? There's only 1 blue left. So this changes. The probability changes. It's dependent. So that's pretty simple. Any questions on that? Okay. So now we're going to go back to these, this idea right here of this complement. Okay, this idea that we're going to look at cases where the probability of A is hard to compute. We're going to use the complement. So here's 2 useful cases right here. So these are 2 cases where, okay, the probability of at least 1, that's hard to compute directly. So these are 2 useful cases of using the complement. And the probability of none is its complement. Okay, and this is going to be easier. Same with not all and all. So here's an example of this. Let's do the same example here with these 3 red tickets. Whoops, look what I just did. I'm going to put another red. I can put the red there, it doesn't matter. 3 reds, 2 blues, and a yellow. Okay, so now what's the probability of drawing 2 tickets with replacement and getting at least 1 blue? Okay, at least. So the question here isn't, with replacement makes it kind of easy, but at least 1 blue. So what does at least 1 blue mean? Well, let's think of what we could get here, what our sample space is. We're interested in, well, you could get no blues, 0 blues. You could get one blue. This is on 2 draws. Or you could get 2 blues. All right? Now, at least one are these 2 possibilities. That's at least one. You can figure it out directly, but it's harder. Whereas this, right here, is none. Just one way. And none plus at least one is going to equal 1, or 100%. So instead of doing this, let's do the complement, okay? Because they have to add up to 1. This one's easy to figure out. This one you could figure out directly, but think about it. You have to figure out, okay, there's 2 ways you can get a blue. You could get a blue on the first, so you could get a blue, and you could do it directly. I'll get a piece of paper if you want to do it. You can do it directly, but you can see what I mean. Okay, so if we wanted to do it directly, it's hard, because what can you get? You could get, here you could get a blue or not blue, or a not blue and then a blue, and then here you could get 2 blues. So you'd have to say, okay, blue is 2 out of 6 times 4 out of 6. Then you'd say, or you'd add those and you'd say, okay, not blue would be 4 out of 6. We put it back times 2 out of 6. And then 2 blues would be 2 out of 6 times 2 out of 6. So you'd add them all up, and what would you get? 8 plus 8, right, plus 4, right? Plus 8 plus 8 is 16, plus 4 is 20. That would be your answer. So you could do it that way, but can you imagine if there were 3 tickets? Then there'd be, how many different ways? There'd be blue, not blue, not blue. There'd be many more possibilities. So an easier way to do this, an easier way to do it, is this is very easy to figure out. So you could say, instead, you could say what? You could say the probability of at least one blue, is equal to 1 minus the probability of none. And that's much easier. It's 1 minus. Now, no blues. No blues out of the 6. How many are not blue? On your first, you're drawing 2 tickets. So how many are not blue? 1, 2, 3, 4 are not blue. So it's 4 out of 6. Then you put that not blue back, whatever it was, and the next one is 4 out of 6. So you have the same thing. You have 36 minus 1636. So that turns out to be 20 out of 36. But I think that's certainly faster. And if you had 3 tickets, it would be much faster. Okay? Do you understand why it's easier? Because there's just one way this can happen, and there's multiple ways you can get at least one. What if we were talking about drawing 5 times? It would be 1, 2, 3, 4, 5. Think about how many possibilities that would be if you wanted to do it directly. Okay, how about let's do the same thing without replacement. So it would be the same thing. How would that change if you do it without replacement? That's the only thing that's changing here. It's the same thing exactly, but this probability of none is going to be what? So now you have the probability of at least one blue is equal 1 minus the probability of none. We're doing exactly the same thing. So that's one. On the first ticket, the probability of not getting a blue is 4 out of 6. But now, let's say we got a yellow. We assume we got it. Now, what's the probability of our next one not being a blue? Well, we only have 5 tickets left, and 3 of them that are not blue. So that would be our answer. So that changes. So these are dependent, and these are independent. But the point that we're making here is whenever you see at least one, there's many ways that at least one could happen. Like, think about it. You have at least one child. Well, you could have up to a dozen children. 1, 2, there's lots and lots of different ways that can happen. But the only possibility, the complement is that you have 0 children. So that's much easier to figure out, and then you subtract it from 1. Does that make sense to everyone? Okay, so let's just do another example with all and not all, which is another one. Probability of not all. So what's the probability? Let's do this. The probability of getting all reds. Well, that's easy. At least one is hard. Let's do. None is easy. This one's easy, all. Because let's think about all. So let's think about, you either get, this is going to be hard. Because you could get 0 reds. Not getting all means 0 reds, 1 red on 3 tickets, 2 reds, or 3 reds. And not all is all of these. These are not all. And this 3 reds is all. So that one's easy. And together they add up to 1 or 100%. So this one's easy, but look at all the ways you can get not all. So this easy one is what? So this is just going to be the probability of all reds is equal to what? There's 6, and there's 3 reds. So it's just 3 6 times 3 6 times 3 6. But what about not all reds? Well, that's where you're going to have to say the probability of not all is equal to 1 minus the probability of all, which is 1 minus 3 6 cubed. It's much easier. This would be hard to figure out directly. Okay, any questions on that? So now, let's see what else we need to do. All right, what's the probability of rolling a fair die twice and getting a 5 and then a 6? All right, these are just simple ones. We'll just do these and then, okay, a 5 and then a 6. So the probability, that's 1/6, you multiply times 1/6. What's the probability of drawing 2 cards from a deck with replacement and getting first a heart and then a club? Well, there's 52 cards, and there's 13 hearts, and there's 13 clubs, but it's with replacement, so it's just that. How about without replacement? Well, this is the probability. Okay, first a heart. It's 13 hearts out of 52. And then you don't replace that heart, so you only have 51 cards left, but you still have 13 clubs left, so that's what it looks like. So this is independent, and this is dependent. All right, so that's it for page 37, and let's move on. Okay, so now I think you can do this page on your own. So let's just complete this one, another on your own, because it's just what we've been doing. So complete on your own for bonus note points. All right, and I'll post it. We can do the first one. What's the probability of drawing 3 cards from a deck with replacement and getting no hearts? This is an easy one. So 52 cards, there's 13 hearts, so there's 39 that aren't hearts, and you cube it. Okay, I think you can do all these. Now, let's see. All right, conditional probability. Okay, so let's see how far we can get on this. So, let me take... We have 10 minutes left. How about? All right. This is going to be a little bit harder, I think. Okay, let me think. All right, conditional probability. The conditional probability of an event B is the probability the event will occur given that event A has already happened. So we've talked about this. So the probability of B given A. So you read it as the probability of B given A. That's what we already talked about. Okay. And we say the probability of B given A is the probability of A and B over the probability of A. And of course, it's only valid when probability. What does that even mean? Okay, what does it mean? So, the probability of B given A. Maybe a picture would help. Just draw this picture. Okay, so you have two events, A, and we'll do a B. And this right here, their overlap right here, is A and B. Their intersection is A and B. So when we say the probability of B given A is the same thing as saying this little bit. If you want the probability of B, given that A happens, so here's the whole, let's say it's in some giant sample space, right? So you have the probability of B, but the probability of, and now you want the probability of B, given that you've already landed in A. So it's this overlap here, probability of A and B over all the outcomes here in A. Once A has happened, that's your tiny probability of A and B over the, so that's what that means. Okay, now when A and B are independent, when A, and we already saw this, when A and B are independent, then the probability of, we just talked about this, B given A is the same as the probability of B. So if they were independent, let's say that would look like, let's say you had A here and B there in some sample space. Well, the probability, well, that's not independent. That's completely dependent. Sorry, this is a bad example. This is harder to draw. Because that would be completely dependent, because if you know A happened, you're sure B didn't. So forget that. This is harder to draw, so I'll do a different way. You know that, you know this already, we talked about it, right? That if A happened when they're independent, it makes no difference. It doesn't affect the probability of B at all. All right, now, let's do, you know, it's very much better to understand this through tables. So let's look at this situation where you have two conditions. If a situation involves two or more conditions, a table is helpful. Suppose a box contains 30 aspirins and 70 Tylenols. Okay, so you have 100 pills, 30 of them are aspirin and 70 of them are Tylenol. So you know these totals here. Then you're told that half the aspirins and 10% of the Tylenols are poisoned. Okay, so half the aspirins would be 15 are poisoned, that means 15 aren't, and 10%, 0.1 of the 70, which is 7, are poisoned, and 20 and 63 are not. Okay? So fill in these first. This is good to fill in the totals first, and then you can complete the chart. The totals that's given here. Now we can add these up, and this is 22, and this is 78. Now it says, what's the probability of randomly drawing a pill from the box and getting a poison? So we just want the probability of getting a poison. So out of drawn from all 100, and the probability of getting a poison is what? How many poisons are there? 22 total. So that's 22%. Okay? So this is total, and this is how many poisons. Now, what's the probability of randomly drawing from the box and getting a poisoned aspirin? So that's the probability of poison and aspirin. both of them. So that's out of the 100 total pills. There's 15 that are both aspirin and poison. So that's easy too. Now, let's look at this. If someone randomly draws an aspirin, there's a 50% chance that it's poison. Where does that come from? Somebody randomly draws an aspirin. So he's already given that it's aspirin. Given that it's aspirin, he randomly draws. Then what's the chance that it's poisoned? So given that it's aspirin, the chance that it's poison is 15 out of 30, which is 50%. Now, does this mean that if somebody randomly draws a poison, there's a 50% chance it's aspirin? So we're asking, is the probability of A given B the same as the probability of B given A? So now this says if somebody randomly draws a poison pill, given that it's poison, so you know it's poison, what's the probability that it's aspirin? Do you think those two things are the same? So let's think about it. So now you know out of the 22, you know it's one of the 22 that are poison, how many of them are aspirin? So these are not the same. So let's just skip this for a minute. Part C was an example showing that the probability of A given B, the probability of A given B is not the same as the probability of B given A. And a lot of people think that it would be, but actually it's pretty obvious that it's not. I mean, can you think of some obvious examples that would convince others without having to show them by doing calculations? I bet almost anything you thought of would do that. Like the probability of being a man, given that you're a human, is what? Given you're a human, the probability of being a man is about 50%. And that's not equal to the probability of being human given you're a man, which is what? 100%. If you know you're a man, you know you're human. So these, the picture for that would be what? You'd have A, like being a man, would be completely contained within human. So of course, they're not going to be the same. So when would they be the same? So one thing that you can think about when they would be the same is this where it might be useful to look at this formula here. So when they would be the same, I'll just do it so when would the probability of A given B equal the probability of B given A? When would that be so? Well, maybe it's useful to then use this definition, because this says the probability of A given B is the probability of A and B over the probability of B. And this is what? This would be the probability of A and B given over the probability of A. So they're going to be the same when these two are the same. This is A and B, same thing. Because look, you could draw it here. If the probability of B and the probability of A are the same, so if A and B are the same size within some larger sample space, then their intersection, this is A and B, is always going to be the same, right? That's A and B. So these two would have to be the same to have them equal. So if we go back to our example, what would have to be the same? The probability of, we're doing poison and aspirin. So the probability of aspirin, which is this, and the probability of poison would have to be the same. Because poison and aspirin is this one. And so 15 over 30 if this was 30, if they were exactly the same, that's the only time that the probability this would be true, unless the probability of A and B is 0. Well, then it would always be true. Like the probability of, so it would have to be when they're the same. So when is it true? When the probability of A is equal to the probability of B, or when the probability of A plus B is equal to 0. Like, here's A, here's B. So, of course, A given B and B given A are the same because there's no intersection. A given B is the same. So this is the idea here. All right. Because the probability of A and B is 0 here. So any questions on that? Okay, so I think it's time to go now. So we'll finish this up next week.